Our next lecturer will be Shruti Puri, and she's going to be talking about bosonic quantum error correction.
So one of the lecture topics is bosonic error correction, and Arne and I will actually be splitting these lectures. So first I'll give a lecture, then Arne, then me, then Arne back. But you can ask any of those questions if you have any. Also, please feel free to interrupt me during the talk. I would rather have this be an interactive discussion. I don't care about rushing through all the topics. I may say some things without proving them, but everything can be proved. So if you want to learn more how to, more details, we can take that up in the Q&A section. If it's something really small, we can do it here, but if not, then we'll do it in the Q&A section. Okay. So in the morning, you heard from Steve about error correction with qubits. So just, again, to set up the language, our qubit is a two-level system, and the two states are ket 0 and ket 1. I'm going to use the notation that the Pauli Z operator is 0, 0, minus 1, 1, and I'm not going to put hats on any of the operators just for convenience. If you are not sure whether I'm writing an operator or just a C number, please ask me, but it should be clear from the context. Then you have the X operator, which is 0, 1, plus 1, 0, and then the Y operator, which is just I, Z, X. And am I writing big enough? You guys can see everything? Great. So, like Steve said in the morning, you can, any valid quantum transformation to the state of a single qubit or many qubit system or any quantum state can be represented in terms of a Krauss map. So you have the density operator under some quantum channel evolves as mi rho mi dagger sum over I, and mi's are your Krauss operators, and they obey the relationship that mi dagger mi, the summation of this, must be equal to identity. And again, like why this is true, like the first time I saw this wasn't very obvious to me. Like how do we go from unitaries to this? So if you're not happy at seeing this, let me know. We can discuss more in the Q&A section. But basically, you can think about that, the environment or some, yes. Did I do something wrong? IXC, okay, sorry. I actually had it by XC, but then I looked at your slides and I thought it was ZX, but it doesn't matter. It's one of these two. So it's plus or minus. Check it out. Okay. So basically this is like some auxiliary system or eavesdropper or environment is interacting with your system of interest, and it's doing some measurements on it. That's where you get this transformation from. Okay. So as Steve said this morning, that if you want to protect a quantum state from errors, then you take many qubits, you encode information redundantly in the state of many qubits. So typically when we think about error correction codes, you have several of these two-level systems, and you and you so say you have n such two-level systems, so you have a large 2 to the n Hilbert space, and you carve out some small space in here which you call your code space. Let's call that C, and this everything else is like your error space. So this is the space that you're going to protect, only a subspace of this whole 2 to the n Hilbert space. And so if the set of, suppose I give you a set of errors, EI. So EI are the cross operators corresponding to some errors that's happening. So Steve gave an example of poly errors. So, these cross operators are like X, Y, and Z operators, identity X, Y, or Z. But in general, this can be anything. So for these errors to be correctable, you need to satisfy an error correction criteria. Steve hasn't done this yet, but maybe he'll do it. I'm not sure. But we can derive the error correction criteria. If you have not seen it before, we can derive it in the Q&A section, no problem. Okay, so suppose the states in the code space, I'm going to write as C sigma. So this sigma is, related to how many states you're protecting here. So then for these errors EI to be correctable, you would want, so you'll have to satisfy the quantum error correction criteria, which is also the nil-Laflamme condition, which is that you would want C sigma, EI dagger, EJ, C sigma prime to be some alpha I j delta sigma prime. Okay, so this is a bizarre looking condition, but if this condition is satisfied, that means these errors are correctable. Yeah. C sigma is just, I'm just representing that to be some states in your subspace of your code space. So C just represents that this is a code space, and sigma primes are basically taking you to different states in the code space. Yes. This has nothing to do with the probability of error. This is just saying that these errors are correctable or not. Right, so let me explain what this criteria actually means. So let's first assume the case where sigma is not equal to sigma prime, because of which this delta becomes 0. So what it says is that when sigma and sigma prime are different, then this must be equal to 0. So to understand what this really means, let's divide this into let's divide this into two halves. So you have a state which is EJ acting on C sigma prime, and you have EI acting on C sigma. So this is some state big psi 1. Let's call this big state psi 2. So what this condition is basically saying is that if you start from two different code words and you apply some errors on it, these could be same errors or different errors. I'm not saying anything about I and J, they could be same or different. Then if you apply these errors on two different code words, then you should go to orthogonal states, because this condition implies that psi 1 and psi 2 must be equal to 0. So the inner product of psi 1 and psi 2 is equal to 0, which means that these two states are orthogonal to each other. So if you start from the code space, then if your errors take you to the states in the error space which are orthogonal to each other, then that error is correctable, and so this is the orthogonality criteria. Yes. Yes. So if you just want to basically, like if you just imagine the code space is only two-dimensional, so you're just protecting a logical qubit space, then this just means that any error acting on the 0 bar indicating the logical code space goes to some state psi 1, and this is some psi 2, then psi 1 and psi 2 must be orthogonal to each other. So orthogonal states, basically 0 and 1, go to orthogonal states. So now let's look at what happens when sigma is equal to sigma prime. And in that case, we have C sigma EI dagger EJ, C sigma is equal to alpha IJ. Okay? That's right. Note that this condition is saying that this object on the left-hand side is independent. The value of the object on the left-hand side only depends on the errors I and j. They do not actually depend on the code words. So basically this means whether you have the code word 0 or the code word 1, this object must be equal to each other. And this is actually the non-distortion condition. So this was the orthogonality condition over here, and this is the non-distortion condition. To really understand, so let me simplify it a little bit. It turns out that the cross, okay, so these, suppose these operators represent an error channel, then I can always make a unitary transformation to get, so I can apply a unitary transformation here to get some other set of error operators, let's call it represented with MIs. And you can always find a unitary transformation such that in terms of the new MIs, this condition actually becomes so here you had alpha ij's. Here that in this new kind of rotated frame or unitary transform frame, the error correction conditions simplify to this object here. The only difference is that instead of alpha ij, I have replaced it with some number chi I, delta ij. So alpha has just become delta functions as well. So the interpretation of the no distortion condition just becomes easier when alpha ij's can be written as delta functions. That is why I'm making this kind of a transformation to show that this is actually possible for any errors. Okay, so once you are okay for me to replace this alphas with deltas, let's call this chi I. Then what it basically means is that if I and j are different, then this vanishes. But when I and j's are, this product vanishes. When I and j's are the same, then and then this guy. So if you just look at this, the top line, for example, what it's saying is that suppose you have a superposition state. So you start with x0 plus y1, and you apply this error onto this state. Then you'll have xe0 prime plus yei1 prime. then let's call this some psi1 and some psi2 over here. Then what you're basically saying is that you are not, because of this condition, you went from this state to this state. But because this condition was true, you did not actually change these coefficients x and y. So you did not distort the state. If this condition were not true, you might have, say, increased x a little bit and decreased y a little bit, or the other way around or something. You would have changed x and y, and so you kind of distorted your states. That's one way to think about it. Okay, so this was a bit of a detour about what the error correction conditions are, which I was not planning to go into, but we can discuss more about this. Okay. So I'm going to keep that there. I can erase this part. Okay, so this is the whole game of quantum error correction, right? Now, if you know a bit about harmonic oscillators, or if you actually read the notes that we provided earlier, then you know that if you have a harmonic oscillator, so it's the Hamiltonian for the harmonic oscillator is, say, omega A dagger A. Again, omega is the frequency of the oscillators, and A and A daggers are operators. So ideally, I should put hats on top of these, but I'm not going to from here on out. A's and A daggers are always operators. Okay, omega is the frequency. So if you have the Hamiltonian of a free linear harmonic oscillator is this guy over here. A and A daggers are photon annihilation and creation operators. The eigenstates of this system are Fock states. So A dagger A acting on N is N are called the Fock states. And the energy is unbounded from top. So these Fock states actually go from n equal to 0 to n equal to infinity, basically. So you can write this as omega n like this. The eigenstates are the Fock states. The energy of the Fock state n, ket n, is omega n. Again, in the notes I may have written here as omega plus half. So I'm omega plus half times A dagger A. I'm not going to keep account of halves there. That's gone. Just omega A dagger A. Okay. So now you already see that the Hilbert space of the harmonic oscillator is large. It's very large, technically infinitely large. See, in a single harmonic oscillator, you can have this construction. You can carve out a subspace of the harmonic oscillator on which you are able to do error correction. Depending on what errors you have, different subspaces might be better for you to choose as your code space. Okay? So let's, okay, so now I'm going to show you a very simple oscillator code, but before that I want to describe what are the errors in the oscillator. So the most common error in the oscillator is single photon loss. Again, like in qubit language, the errors are, we think about in terms of Pauli operators or sums of Pauli operators, or rotation around some axis on the Bloch sphere. But here, errors are in terms of annihilation and creation operators. The most common error is single photon loss, which is that your system is losing one photon at a time to the environment. So if you know a little bit about master equations. Again, you don't need to know that. Just believe me when I write it. Again, we can derive things in detail if you want to. If you have single photon loss, then the density matrix evolution can be written in this form. So rho dot is d rho by dt is equal to minus I h rho plus kappa a rho a dagger minus a dagger a rho by 2 minus rho a dagger a by 2. This part is representing decoupling to the environment, and so this is a single photon loss. Sometimes, so this form is also called the Lindbladian evolution or Lindbladian coupling to the environment, and you can sometimes write this as kappa L a rho like this, or kappa D a rho. Again, in different textbooks, different papers, you'll see different notations. This term here, the term kappa, tells you how much or how fast are the photons being lost to the environment. So if kappa is 0, then this is just a closed system evolution of the cavity, of the oscillator. If kappa is non-zero, then that means that it's no longer free evolution, it's actually losing photons to the environment. Okay. All right, so let's say I have a free cavity, it's our free harmonic oscillator, it's completely linear, it's not interacting with, it has no nonlinearities. The only thing it can do is freely evolve under this guy, and it can lose photons to the environment because of this kind of a coupling. Then, so this Hamiltonian H is just that guy, omega A dagger A. What I can actually do is I can, again, I'm going to jump over some details, but unfortunately I have to. I can't do everything. So what you can do is you can work in the interaction picture of this Hamiltonian. That is, again, interaction picture you must have done in your quantum mechanics class. You basically kind of factor out this free evolution and just look at what's happening because of the other term. So when you do that in the interaction picture, let's call it rho tilde dot just becomes equal to kappa a rho a dagger minus a dagger a rho by 2 minus rho a dagger a by 2. Again, just to save my chalk, I'm not going to write tildes anymore, but just assume that they're there. Okay. It's like an effective A in the rotating frame, or in the interaction picture. Kappa. So I'm saying that this whole thing, this whole like 3 terms, are sometimes written like this. Like as soon as I write L A rho, it means that it's actually A rho A dagger minus A dagger A rho by 2 minus rho A dagger A by 2. It's the same thing. It's the same. So people use this notation or this notation or whatever. So usually, like you might for any system, you might actually want to write something like D sum operator O rho, which effectively means this guy means it's O rho O dagger minus O dagger O rho by 2 minus rho O dagger O by 2. That's it. That's fantastic. Okay. So now, in terms of your Krauss operators, you can write that the channel in terms of Krauss operators is basically E rho, which is basically what is it under this evolution, what is the density matrix after some time t. That is just equal to summation of, again, your Krauss operators, mk, rho, mk dagger. So this is rho initial, this is rho final. And your mk's are basically square root of 1 minus e to the minus kappa t n divided by n factorial times e to the minus kappa t a dagger a by 2 times a to the n. Okay, so there are actually some, this summation over, oh sorry, this is, okay, and this is, actually maybe I shouldn't use the notation k because k and kappas look the same, so I'm going to call this actually just m. Okay, so this summation n again goes from basically 0 to infinity, right? So this is like, the channel is like an infinite sum over these Krauss operators. T is the time. So if you want to look at what happens after 10 microseconds or 100 microseconds or whatever, that's the number you're going to change. And kappa is basically how fast your environment is coupled with your oscillator. Okay. So if I assume that I'm going to be doing, eventually when you do error correction on the system, you're going to be checking for errors very frequently. That means you're only going to let this system evolve for short periods of time before you check for some errors and correct it. That means this kappa t you're going to assume to be small. So you're going to assume kappa t to be small, so much less than 1. And in that limit, in terms of, in small kappa t, the terms that are important, or the higher order terms, are just basically m0 and m1. And then m2, m3, etc. actually decrease with, kappa t to the power of n. So just for small kappa t, I'll just write what m0 is. That is just, well, that's fine. That's minus kt a dagger a over 2. m1 is square root of kt e to the minus kappa t. And then when you write m2, you will have a like a kappa t here, and a square, and so on and so forth. But you see, you're increasing these powers of kappa t. Here, there's no power of kappa t. Here, there's square root of kappa t, then just kappa t, and then the next term will be kappa t to the 3 by 2, and so on. So basically, as when kappa t is small, as n increases, these higher order terms become smaller and smaller. Now, what do these higher order terms actually mean? Okay, just for a second, let's start with m1. m1 has something over here, this part. And then there's this term over here, which is a. If you remember from the notes, a acting on a Fock state n takes you to the Fock state n minus 1. Right, so a acting on n, if you remember, was square root of n minus 1. Right, so the a operator actually removes photons from your system. Single action of a removes one photon from your system, or one it removes one excitation from your harmonic oscillator. If you're at A square, then that would remove 2 excitations, right? You went from n to n minus 2 and so on. So what that statement is actually, what that math is actually saying is that for small kappa t, the probability of losing more than 1 photon is small. Like you're just basically saying that the probability to lose 2 photons goes as kappa t, the probability to lose 3 photons would be kappa t to the power 3 by 2, probability to lose 4 photons would be kappa t square, and so on and so forth. And for small kappa t, the probability to lose more than 1 photon, I can basically just suppress. Okay? So most of the time what's happening in the cavity is that, or oscillator, harmonic oscillator, is that you're losing 1 photon at a time to the environment. Now if you look at what this term does, basically e to the minus kappa t a dagger a over 2, that doesn't change the photon number at all. That's just the Fock state is an eigenstate of a dagger a. So that doesn't remove photons from the system. If you have done quantum optics or you will plan to take a quantum optics course in the future, sometimes, okay, you can relate this M1 and M0 terms also with the jump and no jump evolution of the system. When you do quantum Monte Carlo and things like that, you will learn about jump and no jump evolution, and it's kind of related to that as well. Okay. So hopefully by now I've convinced you that the most common errors in the system, in the harmonic oscillator, are going to be M0, that is no jump happening, and then M1, which is like okay. Again, this is to an approximation. So now, once I have this, once you trust me that this is what's going to be happening mostly in your harmonic oscillator, now let's look at a code. Okay? Where a simple, yeah. Yeah, you have to have this. So that cross operator is for this evolution, nothing else.
Okay, so you,
if you're given this, then that's your cross operators. You can have more, if you have a more complicated Hamiltonian here, then that's not necessarily that cross operators you're effectively going to get. This was specifically an oscillator evolving freely. It's completely linear, it's evolving freely under this Hamiltonian A dagger A. That's when you get that cross operators. In general, more complicated systems, it won't be. So I will get to something called as a Kirkat, for example, and in that case, that's not the cross operators. Yeah. Yes. So you do. What to do about that? Well, it doesn't. So what I'm going to get to you is that I will be able to correct for only these errors, and the other errors will not be correctable. I mean, even this. Basically, what I'm going to show you is that errors to the order of kappa t will be correctable. Anything else that's uncorrectable will be of higher orders of kappa t, and so those will be uncorrectable errors. But it's what I'm going to show you is a first order code. So yeah, it only corrects for a single photon loss, nothing more than that. But that's similar to, for example, the quantum repetition code example that you saw. You were only going to, for a 3-qubit quantum repetition code, you're only going to correct for 1 errors. It cannot correct for 2 or 3 errors and so on. So it's kind of a similar way. This is only going to correct for single photon loss, but nothing else. Okay. So a simple code, which is the smallest, what we call binomial code. So there's a class of error correction bosonic codes, which is called a binomial code. And I'm going to show you an example of just the smallest binomial code, which is, so the zero logical is given by superposition of Fox state 0 plus Fox state 4 divided by square root of 2, and the one logical is just the Fox state 2. I want to just stop here for a second and specify. I'm using a harmonic oscillator, but at the moment I'm still making a logical qubit out of it. So I'm encoding a qubit in a harmonic oscillator. There is work on encoding a harmonic oscillator in many harmonic oscillators, but that's not what we're going to talk about. We're only going to talk about encoding a qubit in a harmonic oscillator. So I'm still error correcting a qubit subspace. Okay. All right, so here are my M0s and M1s. So let's see, M0 acting on the state 0. If you were in my course, I would have somebody do this on the blackboard, but I'm not going to subject you to that right now. But if you want, you can shout the answer. Can somebody tell me what is M0 acting on the 0 bar state? Yeah, so what is this guy acting on this guy? Just somebody shout. That'll be reassurance that you are here listening. That's all. So 0 bar. So this is 0 bar, right? So that's just. I'm sorry. That's just 0 plus e to the minus 2 kappa t 4 pi. Did I do everything correctly? Okay. Okay. And then I have M0 acting on 1 bar is e to the minus kappa t 2, right? Is that okay? And then I have M1 acting on 0 bar is equal to what? Prefactor? All right. So that'll be square root of 4 by square root of 2. There you go. So I don't make any mistakes. So square root of 2, 3. If I make a mistake here, please let me know. I'm not looking at my notes all the time, so I may make some mistakes. And then you have M1 acting on the 1 bar state, and that is square root of 2 acting on the Fox state 1. Yes, did I? It's 0. So it's a null, yeah. It's a null vector. Yeah. Sorry? Oh, did I miss it? Oh, there you go. Thank you. This is e to the minus again 2 kappa t. You're right. Thank you. And this one is Did I do some? Sorry. Oh yes, sorry. Square root of kappa t and square root of kappa t. Is that good now? Are we good? Did I do something? This by 2. Okay. Good. Yeah, I did it correctly here. Okay, so now let's see if the error correction criteria are satisfied. So remember, the first thing I want to check is that, okay, so what was the error correction criteria? It was that I want 0, EI dagger, EJ, 1 to be 0, right? And that is actually true over here. You see that M0, so you see this has only even photon numbers in it, even Fock states in it. Similarly, this is an even Fock state. M0 and M1, sorry, M0 doesn't change the Fock state itself. It preserves the number. So it keeps the even Fock states to even Fock states. M1, on the other hand, will change even to odd, right? So this is identically going to be equal to 0. Right, so if you have, so you can check this. Did I miss anything? I think I covered everything. So this will be 0 all the time. And then we have the other condition, which is I have to look at what happens to 0, yeah, dagger, EJ 0, and 0, EI dagger, 1, EI dagger, EJ 1. Okay. So if EI and EJ are different, then both these are equal to 0. Sorry. That's right. Okay. Yeah. Both of them are equal to 0. If so, for I not equal to j, you have 0. But for I equal to j, what happens? So if you have 0, say M0 dagger, M0, 0. Second bars here. Okay, let's look at that term. So you have this guy inner product with itself, and so I'll have 1 over 2, 1 plus e to the minus 4 kappa t. And if I have 1 bar, M0 dagger, M0, 1 bar, this is equal to e to the minus 2 kappa t. Sorry, can you say that again? In this one? So I'm going to do this guy, right? So 0, 0 is 1 and 4, 4 is e to the minus. Yeah. Good. Right. So this criteria, we should, for the error correction criteria to be satisfied, this and this should have been the same, but they're not. This is actually, again, for small kappa t, this is 1 minus 2 kappa t, and this is 1 minus 2 kappa t plus other terms, other terms higher order in kappa t. So to first order in kappa t, they are the same, but to higher orders in kappa t, they are not the same. Right? So again, if we are just looking at correcting things to the order of kappa t, the lowest order, then my correction criteria is still satisfied here. To higher orders, it's not. And so you can again check this also for 0, M1 dagger, M1, 0, etc. So you'll see that all the error correction criteria are satisfied to the lowest order. And so this is a valid code which corrects for single photon loss. Is that okay? And again, this code was made in a single oscillator. The price we are paying is that we have to create these up to 4 photon Fock states. So we have to create this superposition state, for example, and this Fock state too. But if we are able to do that, then this is a valid code. Any questions? Yeah. This one? This one? Yeah, this is 1 plus e to the minus 4 kappa t. So, yes. Yes, I'm just calculating this guy over here. Yes. Is it not? M1 is this guy. 2. Yeah. This one? This should be minus 2 kappa t, you're saying? Let me check the math and get back. But to first orders, it should be satisfied. I'm going to check the math and get back. Yes. Not for this code word. So the other cross operators are like already higher order in kappas, and we are saying that this code will only correct for single photon loss, not more than that. Okay, so you can extend this binomial code to correct actually more photon loss, 2 photons, 3 photons, n photons. You can generalize this more. You can also generalize it to correct for photon additions. You can also generalize it to correct for dephasing errors. So dephasing errors is like errors that have like a dagger A's in them. So like this guy over here. Okay. So what is the problem here. So the problem is that you have to prepare these states. You have to prepare these highly non-trivial states in an oscillator. In particular, these are what are non-Gaussian. In particular, these are non-Gaussian states. And yeah, so you have to. It's hard to prepare these states. You have to. You can't prepare these states in a linear cavity. You have to have some nonlinearity somewhere to be able to generate these states. Where should I erase? So the most the traditional kind of approach to prepare these states is by taking say a cavity and coupling it with a nonlinear system like a two-level atom or a transmon qubit or whatever your favorite qubit is, and use the coupling between this oscillator, infinite dimensional Hilbert space, and the two-level space of this qubit to actually generate arbitrary states in the oscillator. In particular, in superconducting circuits, you actually have a superconducting cavity, and it's coupled to a transmon qubit, and you use that transmon now as a control for your oscillator. So you use this is the nonlinear system now, and you use this nonlinearity to kind of effectively make complex states on this cavity. But without this, and just using a linear cavity, you cannot prepare these states. So I think next week you will be hearing talks from Vlad and Alec, who will be telling you in more details about how you can prepare some of these complicated binomial code states using a superconducting microwave oscillator coupled to a transmon qubit. The other way to do this is have your nonlinear, instead of using a linear oscillator, use a nonlinear oscillator itself. So the Hamiltonian, I don't know how to draw this. Never mind. So let's make it like this to show that it's nonlinear. But basically, the Hamiltonian is not just simple omega A dagger A, but it can have some nonlinear terms such as you can have cubic terms, you can have quadratic, you can have quartic terms. Let's call this chi1. You can have some quartic terms, and so on. So if you have a nonlinear system, you could try and make these states. So Arne will actually talk about the GKP codes, which are currently in superconducting circuits or even in atomic trapped ion systems. They kind of are prepared this way, like you have a control two-level system that creates some non-trivial state of an oscillator. But what I will talk about today is the Kerr-cats, which fall into this category. Those Kerr-cats are made in a nonlinear oscillator itself. Okay, it's there are proposals to build GKP states, for example, with highly engineered nonlinear Hamiltonians, but we won't go into that. I'm just going to talk about a simple Kerr-cat qubit. Okay. Okay, so the Hamiltonian that we will now be looking at is a Kerr nonlinear Hamiltonian. So the first term is just the frequency term. This is what you're familiar with. The second term is the nonlinearity, which is this interaction over here. So it's a dagger square a squared. In terms of number operator, you can write this as omega n hat plus ker n hat times n hat minus 1. So the Fock states are still good eigenstates of this system. However, now because of this term, the eigenenergies of the Fock states have changed. So Fock state 0 has still 0 energy. Fock state 1 has still the energy of omega. Then you have Fock state 2, which now has the energy of 2 omega plus 2 ker. Then you have Fock state 3, which is 3 omega plus 6 ker. And so on. Did I do something? Is it 6 ker? You made a face, so this is fine. Oh, sorry. Yes, I'm sorry. You're right. Here, this one. Yeah. There you go. And so the gap, this gap is omega. This gap is omega plus 2 ker. This gap is omega plus 6 ker, and so on. So now this gap is changing. It's not the same gap between, Fock states that differ by 1. The gap itself is changing. So this is a nonlinear oscillator. So one way, what you can actually do is, a simple way to encode a qubit in the system is actually just, call the Fock state 0 and Fock state 1 as qubit 0 and qubit 1, and that's just your qubit. In fact, that is what a transmon is. So you can just work with these two states as qubit 0 and qubit 1. Again, you won't get any error correction benefits from here. It won't, like a single photon loss is going to bring 1 to 0. So you clearly see this. You're not actually using the dimensionality of your Hilbert space to do anything better for error correction at the moment. But just wanted to tell you that if you just use the lowest level, you get like a normal regular qubit, which is actually also, this is exactly what a transmon qubit is. But why is this nonlinearity important? This nonlinearity is important because now you can, say if you start from the vacuum state, you can prepare the one state deterministically without, going to these other states at all. This is why this nonlinearity matters. So what you can now do is, suppose you have the vacuum state 0, and I ask you to prepare the qubit in now state 1. How will you do it? One simple way to do this is just add a linear driving like so, and I will apply it at a frequency of omega t, omega. So suppose the frequency of this drive, so this is a classical drive. Just imagine a laser driving your nonlinear mode. So if you apply such a classical drive at the frequency omega, which is same as the frequency of the oscillator here, then this will actually only drive the qubit from the state 0 and 1. And to really see that, what we're going to do is, I won't derive everything, just like kind of give you qualitative way to understand it. So the first thing you will do is something called the rotating wave approximation, which is essentially a fancy perturbation theory. Once you do that, and then you can write, and you work in the interaction picture of this guy. Of omega a dagger a. Sometimes instead of saying interaction picture of omega a dagger a term, you can just say you work in the rotating frame, which basically means that you just say you work in the rotating frame, rotating at the frequency omega, which means that you basically are kind of factoring out the effect of this term over here. this is, so this is just a nonlinear oscillator. This is, I'm applying a classical electromagnetic drive to the oscillator. So suppose, you have two electromagnetic modes. So classically, you have like a E1 times E2 interaction between them. That quantum mechanically, if one of the electromagnetic fields you want to treat quantum mechanically, then this will be the effective Hamiltonian. That's like the control. So imagine like you have an optical system. So you're applying a laser at this frequency. If you have a superconducting system, you're applying a microwave drive to it. Okay, importantly, this is just a simple linear drive. So once I make the rotating wave approximation, and I'm going to just work in the interaction picture, my Hamiltonian is, again, removing all the tildes, is basically Kerr A dagger square, A square plus epsilon A dagger plus A. I think you will get a factor of 2 here because of the rotating wave things, but I'm just going to call epsilon by 2 as J, whatever, it doesn't matter. This is where I want to get to, okay, from here to here. So now you see, what does this guy do? Fox states are the eigenstates of this guy, and in this sense, you have the Fox state 0 and Fox state 1 are actually the same energy now in this new interaction picture frame. Then you have Fox state 2 over here, Fox state 3, 4, etc. This is 2 Kerr, this is 4 Kerr, I believe, in terms of the difference, and so on. Okay. So if I start from the vacuum state 0, then this term doesn't do anything to the vacuum state, it's just the eigenstate. This guy, A dagger plus A, acting on the vacuum state, A doesn't do A is just going to, remove that term. A dagger acting on 0 will take me to the 1 state, right? So this will take me to the 1 state. Similarly, A dagger plus A acting on the 1 state will take you to the 0 state and the 2 state and so on. Right? So basically where I'm getting at is so if you look at the Hamiltonian, you have H equal to summation of n minus 1, and this is just times Kerr. This is just the Kerr nonlinear term. Then you have A dagger plus A, which is going to couple you between the different Fox states. So A dagger is just n minus 1 square root of n. Let's put this J here, plus the Hermitian conjugate of that. Okay. So let me first just limit myself to these 3 states, just for convenience. If I just do that, then I have 2 Kerr times 2, plus there'll be terms I'm missing. I'm going to not write some prefactors, but you'll have something between 2 and 1, plus something between 1 and 0, plus the Hermitian conjugate, right? Some factors of square root of 2's or whatever I'm not writing. So if you look at this now, if you start from the vacuum state and you do perturbation theory, you will see that you will only, this drive term will only take you from 0 to 1. the rate or the probability with which you go from 1 to 2 is now going to be suppressed by j over 2 kerr square. There may be like square root of 2 somewhere there. So maybe there's a square root of 2 here. Right? But you basically get this penalty of j over kerr. You would not have this penalty if you did not have the nonlinearity in it. So now, now this is why I say that to have a qubit, you need some nonlinearity, because that will allow you to manipulate within your qubit subspace. If you start from vacuum, if you start from vacuum, you can just apply that drive and go to the 1 state. The probability that you leak out to the 2 state will be small. So the bigger you make the nonlinearity, the further you're going to suppress any leakage to these other levels. Okay, so this is basically how even a transmon system works. So now I'm going to tell you how to modify this Hamiltonian and get to a Kerr-Cat. It's a bosonic qubit, which is more complicated than just the 0-1 encoding over here. And it actually has some protection against noise. So for the Kerr-Cat, the Hamiltonian you begin with is this one. Now I'm going to add something slightly more complicated than that linear drive. I'm going to add a quadratic drive. And I'm going to add that drive at twice the frequency of this guy. So notice the difference. This versus this guy. This guy can only add or subtract photons by 1. So basically, you are exchanging 1 photon at a time with your laser or whatever. Here, though, you are able to add or subtract 2 photons at a time. This term will, for example, take you directly from 0 to 2, 2 to 4, and so on. This is called also a 2-photon drive or parametric drive. How you actually get this in superconducting systems, I think Alec or Vlad are going to go into it, but I'm also happy to tell you more about how physically you obtain this drive. So again, I'm going to do RWA, the rotating wave approximation, again fancier perturbation theory, and I'm going to work in the interaction picture. Of this guy here, so that my Hamiltonian now becomes Kerr A dagger square, A square plus some epsilon A dagger square plus A square. This, there may be a factor of 2 here, so I'm going to just call this J. Now, if you notice one thing, you can factorize this Hamiltonian in this form. Yes, this is exactly written out in this. If you multiply this out and open the brackets and stuff, you'll see that they're exactly the same. Okay, so who remembers coherent states from notes? that we sent earlier. Yes. So what are coherent states? Right. So CAD states are superposition of coherent states. That's true. So a coherent state is yes. Coherent states. So the coherent states are eigenstates of the photon annihilation operator, right? So A acting on alpha is alpha times alpha. So coherent states are eigenstates of the photon annihilation operator, and in terms of Fock states, they are. Okay, I'm not gonna. Hopefully, I get this right. Minus alpha squared by 2. This is right? I think so. Okay, good. Okay, so if you now notice that there'll be two coherent states, I alpha and minus, okay, actually, so there'll be two coherent states, alpha and minus alpha, where alpha is I square root of j over k. Okay? If you consider these two coherent states, alpha and minus alpha, where alpha is particularly equal to alpha is equal to I square root of j over k, where j and k are what appear over here, then you see what is a square acting on alpha. A square acting on alpha is just alpha square alpha, which will be, this guy square is minus j over k alpha. Right? A square acting on alpha is just alpha square. Similarly, a square acting on minus alpha will also give you minus j over k minus alpha. So now, if you look at this Hamiltonian over here, then you have a square plus j over k. Suppose if you a square plus j over k acting on plus and minus alpha, if you use this, then a square plus j over k acting on plus and minus alpha is basically 0 times plus or minus alpha. That means that Hamiltonian H acting on plus and minus alpha is equal to minus j square by k plus or minus alpha. So these two coherent states, which have the same amplitude but different phases, are the eigenstates, or the degenerate eigenstates of this Hamiltonian. Okay? That means that they're even an odd superposition. So these coherent states are not orthogonal to each other, but you can, the following states are let me write the normalization constant actually. Square root of 1 plus So if you take these superpositions, then these are the even superposition and the odd superposition are exactly orthogonal. And you can actually treat them as qubits. So this is, you can call this as qubit 0, and you can call this as qubit 1. Yes. Yes. Another way to look at it is that you can write the coherent states in terms of the Fock basis and do a little bit of math, and you will see that the even superposition state will have only even Fock states appear, and the odd superposition state will have only odd Fock states appear. And it's because of this. So basically, just use this expansion. Then you'll see that for the even superposition states, odd n terms will cancel out, and you'll get only even Fock states. And for the odd superposition state, even n terms will cancel out, and you'll get only odd Fock states. So this is a even parity state, and this is an odd parity state. Parity is, you can define a parity operator for harmonic oscillators. So you have parity operator is just exponential I pi a dagger a. So these states are the +1 eigenstates of the parity operator, and this is the -1 eigenstate of the parity operator. So in fact, in superconducting circuits, what people have done and can do is that you can measure parities. You can measure these things, and you can check whether you have an even parity state or an odd parity state. Okay. Now, so this is the Kerr-Cat qubit. It is realized in a 2-photon driven Kerr nonlinear oscillator. It is not a logical qubit in the sense that if you have a single photon loss, it doesn't satisfy the error correction criteria for a single photon loss. You can immediately see that, because if you call this 0 and this as 1, the A acting on the 0 state will take you to the 1 state, and A acting on the 1 state will take you to the 0 state, and you won't satisfy the error correction criteria. So then why am I even talking about this? Because the whole speech to you before was that you can, realize this protected code space in the big oscillator Hilbert space. I will show you this in the next time we meet, is that the Kerr-Cat qubit is not protected against single photon loss, but it is the common errors in the oscillator will cause 0 to go to 1 and 1 to go to 0. So it will cause these parity flips. So it will cause, in this term, X errors. But it will not cause Z errors. So it will not take you from 0 plus 1 to 0 minus 1 and vice versa. Or the probability that this error happens, this is like a Z error. So the probability that a Z error happens is exponentially suppressed compared to the probability of this error happening, a bit flip error to happen. So the error channel is kind of simplified. So Steve Flemia today morning showed like the depolarizing error channel, where which is what people usually study, which is the error channel on a single qubit is like 1 minus p rho plus p by 3 x row x plus p by 3 y row y plus p by 3 z row z. But what the error channel of this qubit is going to be actually just 1 minus p row plus p x row x. It is not going to have any, the probability to have a y or z error is going to be exponentially suppressed. So because you're kind of inherently correcting for y and z errors, your error correction on top should become easier. That's the whole point. The error correction, like if you now treat this as a qubit and put it in the quantum repetition code, it should work. You only need a quantum repetition code for this to work. In reality, of course, in our real systems, y and z errors are not zero. They're small, but they're not zero. So you need to correct for some y or z errors, but your code by itself will become simpler because the y and z errors are much less likely than x errors. So such systems are called bias noise, where one error is more dominant than the other errors, and the error correction there becomes simpler if you have certain operations that also are biased. We'll come to all of that in the next lecture. I will warn you that the reason I chose this convention is because the experimentalists are going to, next week when Alec and Vlad show you some experiment results on the GERCAT, and they'll actually show to you that the error channel is actually biased. This is the notation that they use. So their block sphere is so they draw their block sphere like this. So z, x, y. So the z-axis is alpha plus minus alpha. And minus z is alpha minus minus alpha, and the normalization constant. And the x-axis is just simply 0 plus 1 over square root of 2 and 0 minus 1 over square root of 2. So in their language, the z and y errors are suppressed compared to x errors. So bit flips are dominant. So if you see experimental papers on GERCATs, this is a block sphere they all use. If you use theoretical paper on GERCATs, we rotate the axis by 90 degrees. For theoretical papers, we actually put the even parity cat state along the x-axis, the odd parity cat state along the minus x-axis, and their superpositions, let's call this plus and minus, so the superpositions appear here. This block sphere is just 90 degrees rotated with respect to this block sphere. I'm sorry. But so in theory papers, you will see that the x and y errors are suppressed compared to z errors, because we just chose to rotate our block sphere by 90 degrees. So there's a reason the experimentalists choose to do this to do it this way. We prefer to do it this way. They're the same. It's just 90 degrees off from each other. So I will try to keep my language the same as what the experimentalists will talk next week. But if you look at theory papers, this is what we'll use. Okay, so I'll stop here and take questions. You had a question? I think we have a few minutes. I can take questions or, yeah.
So just to like big picture. So from what I understand, you always started with some non-linear Hamiltonian, and then you added this like drive thing, which sort of created a degeneracy between the 0 and 1. So is the drive in essence an
Yes, that's one way to think about it.
So then how is it? So is it encoding, but at the same time it's also manipulating the noise?
Right. So if I just write this Hamiltonian, then it's right now not manipulating anything because my qubit states are degenerate eigenstates of this whole Hamiltonian. So if you prepare one of the eigenstates, it's not going to change to the other. I mean, if you prepare the cat plus state, this state, it's not going to change to this state because it's an eigenstate, it will remain there.
Yeah, so like how did you come to this conclusion about the Z errors being exponentially supervised? Like, where did that?
I have not explained that to you yet. I'm giving you yes, and I'll tell you next time why that is the case. Yes. So this is, in fact, you should think, one way to think about this is that this is in itself an error correction code that protects you against, in this language, okay, in this box here, Z and Y errors. So this is an error correction code against Z and Y errors. Why? I will explain that next time. Yes. And you can actually even have a notion of distance and thresholds even here. Okay, I can take more questions in the Q&A section.